Pavitra, we can start then. Let us start.
Yeah, sure.
Yeah. So, welcome to week 11 live session of molecular spectroscopy, our physical chemist perspective. Today we are going to mainly discuss today we are going to finish the electronic spectroscopy, electronic transitions. And before doing that, we will discuss a little bit about the rotational fine spectra and their how what are the selection rule, and due to the selection rule how the portrait diagram or this band origin or band head, that concept comes in. And then we will go to the symmetry of electronic states, how to determine that what is the symmetry of a state, electronic state, like for oxygen and benzene has been discussed in the class. We'll discuss those only. And then we will look at the absorption spectra of the benzene and try to means assign that which transition is due to which band is due to which transition. So like that we'll do, and then we will solve the week 10 assignments. And on the next week, actually, we are going to have only one class, but two assignments and two lectures of 2 weeks will be remaining. I'll try to cover the 2 weeks, next 2 weeks in the next live session, and we'll cover that accordingly. That is about the NMR spectroscopy. So we can, there are I think 6 lectures are left to discuss about that, and we'll do that on the same day. But now let us start with today's material. So to start with, we will discuss the rotational fine spectra, what we have discussed. But before that, also let us write down the transition moment integral that would be the responsible for a electronic spectroscopy, and when we will follow. So Born Oppenheimer, sorry, approximation is valid. That means one approximation is valid, then actually we can distinguish between, means we can take the product
In the
of, right, we can take that wave function separately, right? And due to that, will be able to write the transition moment integral TMI as. So today I will write it in a integration formula. So one will be related to the spin state. So psi s of the, so this is the spin part, the tau s. Then there are electronic parts. But before that, if Born-Oppenheimer approximation is not hold, then so this is over spin, this is over vibronic state, and this is maybe the electronic space part. So I first will write them together. IV dash electronic dash mu IV double dash d tau. So this is your this can be also be we can write it in terms of vibronic. We can write the first. So when the Born-Oppenheimer approximation is valid, we can write it like this. And when it will not valid, when not valid means some due to some perturbation. Suppose there is some electron. So that is the thing we are going to learn in the upcoming slides. That when there is some perturbation due to which there is going to be a coupling between the vibronic states and the electronic states, then they are no longer separable. So then you will use this, right? And that will only so that due to that vibronic coupling, that uh, a transition will be allowed, but due to vibronic coupling, but it will be very weak comparable to a orbitally allowed transition, and that will only be seen when that is not there. I will come to it in a bit. So these tau E are the volume elements. So these actually first part, this actually depend if the transition is been allowed or not. So or forbidden. So that is depending on the, and we know the delta S should be 0 and delta ms also should be 0. Delta S should be 0 means the total spin, that is your singlet to singlet and triplet to triplets are allowed, spin allowed, right?
Yes.
So that is one.
Yes.
And this part gives you the Frank Condon factor, that is your uh,
Direct upward tension.
yes. So this gives you the overlap between the wave functions, vibronic wave function of two different electronic states, right? So
Yes.
it depends. So 0 to 0 will be much more stronger, or 0 to 1 will be stronger. That or 0 to 2 will be stronger. That will depend on how much overlap is going to be there. And this is orbital. So this will depends if the transition is orbitally allowed or not. And how come this will be judged? This one, how come this will be judged? You need to look at if the triple product, same here also, a triple product should be symmetric. Symmetric to become allowed. If it is anti-symmetric, the triple product, then what will happen? Then the integrand is your anti-symmetric. That means if you change uh, mm, the starting point and the end point, means in the definite integral, if you change the sign, then it is going to be negative,
Yes.
and then your integral is going to be 0, and that is
Yes.
only possible when your triple product is going to be 0. So your TMI is going to be 0 if your triple product is anti-symmetric. So it has to be symmetric. So these are the factors, and the most stringent factor is that your it is has to be spin allowed. Okay, if it is not spin allowed, then your transition will be the intensity will be very less. Then next parameter would be the orbitally allowed or not. Allowed and orbitally allowed would be most highly intense, and then the vibronic Frank Condon factor will come into place, that how much overlap is there or not. And if they are not allowed orbitally, even though they are allowed spin, if they are not orbitally allowed, we have to look at this part, that when bond moment approximation doesn't hold, then there is going to be some perturbation, due to which there will be a coupling between the vibronic state and the electronic state, due to which we have to look at the product of all these, and similarly that product has to be symmetric to become your uh,
Non-zero
orbitally,
T.
yes, non-zero TMI. Good. So with that, let us start. So we yesterday we have learned about the electronic spectrum, and now let me a little bit give you some idea about the rotational spectra, how the rotational spectra finds spectra, rotational. Sorry about that. So this will observe with very high resolution of your instrument. So the equation is delta epsilon is something like your new bar is obviously there is a transition between your vibronic states, and there is going to be your change in the this rotational energy, right?
Yes.
And why do I keep the B inside the delta?
B value will change.
With the
B.
electronic states, right? So if
Yes.
my in the excited state, if it is suppose this is B dash, and in ground state it is B double dash, and suppose your bond length is more in the excited state than the ground state, then your B dash is going to be smaller than the B double dash, right? So that is
Yes.
already known. Now, so how can we write this? The next part, mu EV, we can write it B dash J dash J dash plus 1 minus B double dash J double dash J double dash plus 1. Now here comes an interesting thing that we know that there are three selections rule, right? Delta J could be 0, delta J could be plus minus 1, and delta J would be 0 and plus minus 1 for any transition, but other than apart from only one, that J dash and J double dash cannot be 0. So for J dash and J double dash other than 0, delta J can be 0 and plus minus 1, and delta J will only be plus minus 1 from singlet sigma to singlet sigma. So I'm not writing this, but we have three cases, right? In one case, delta J can be 0. In that case, if delta J is 0, that means J dash minus J double dash is uh, 0, and that eventually means your J dash is going to be J double dash. So your new bar, suppose I am writing Q, so that is your new EV plus, and it is going to be B minus, this is very easy, the first one, J dash, or I can write even J double dash, whichever I can take. And can you tell me what should be the value of J dash here? What are the possible value of J dash?
It can take any values except 0.
Very good. And that can be 1, 2, 3, anything but not 0. So this is your Q band. So there are two more band, P, Q, R. Q is in between, right? And what about delta? If delta J equals to plus 1, that means your J dash minus J double dash is plus 1. And that eventually means your J dash is equal to J double dash plus 1. So your new, so I'm not writing it now that what is it is going to be. I think you know PQR, right? So
Yes.
du EV plus, now I will just write it a little more. So J dash. So one can write it in terms of anything, J dash or
Yes.
J double dash. It doesn't matter.
Yes.
Uh, I think in the class sir has done it with respect to J double dash. Just you need to remember that what could be the possible values of J dash or J double dash. That is important. And then it would have been B double dash. J double dash is going to be J dash minus 1, and J double dash plus 1 is going to be J double dash. J, sorry, yes,
Yes.
J. Now we can actually take, can actually write it in detail. Am I making any mistake? J dash minus 1. I think so. I'm B dash J double dash J dash plus 1, and here I have written, acha, so I have to write it in terms of maybe J double dash. Let me check once.
If you are converting into J dash or J double dash, it doesn't matter. You have to convert all these things into J dot or
Right,
maybe
only
J double.
any one of the
Yes,
things,
yes,
right?
yes.
So let us first take the one common in terms of j dash square, that is going to be your b dash minus b double dash, right? And then we can take in common of j dash, that is b dash plus b double. So that is one of the thing. And here your j dash have the possible values. What do you think? The possible values of j dash?
J dash can take this one, 2, 3, 4,
Why not zero?
0. If it takes 0, then J double prime will be minus 1.
Mm, j double minus if j is zero. Oh, right. So your j double dash can be zero, but j
Yes,
cannot be zero, right? Right.
yes,
It should have been start from one, two, three, right? So better, I think, write in terms of j double dash, but I think as you already told me, you already got the idea. So I'll not go in that. Maybe delta j equals to when it is minus one, then j dash minus j double dash is going to be minus one, and that means j dash is going to be j double dash minus one, or maybe I can write j double dash is going to be j single dash plus one. So nu p, nu bar p is going to be nu bar ev plus b dash, j dash is going to be your, so this is actually single, so your j dash plus 1 minus d double dash, j double dash would be dash plus 1, and this is going to be j dash plus 2. Am I writing it correctly?
yes. Sure.
J double dash plus 1.
Oh,
So j dash and j dash plus 1, j double dash plus 1. J double dash is j dash plus 1. So let us break it down and then only we will understand.
yes, yes.
B j dash square plus j dash and b prime, acha, wait, square plus 3j plus 2, right? Something like that. J square plus 1j, 2j, like this. New EV plus bj dash, b double prime, j dash square minus 3b double prime j dash minus 2b dash. I think this is something. So actually, your, so this is, so I think as we are doing it like that, we have to take something that minus 2. So minus 2, I think. So the best way it would have been to keep all the terms in terms of j double dash. But
Okay.
but let us try something different. Huh? Here let us see if we have 1, suppose. Huh? So that one could lead to j double dash minus j dash is 1. So suppose instead of 1, suppose nothing is there, let me write it like this, in hope that something will prevail. If not, then we will come back to our old uh, thing. It would have been 2b dash J dash, J double dash. 2, there is nothing like that, and it will be 2B double prime J dash. Something like this is there, 2B double dash. Huh, here, see, 2B double prime J dash. So we can take only one.
Okay.
So I can cancel that, right? And is there any opportunity where I can, so the J prime is also there, and uh, J that thing is also there. What is called your J prime is also there, and J double prime is also there. So maybe we can change the problem in terms of J prime, J double prime. I thought I will give it a try with that. That if so, your delta epsilon is new bar, or this is your P band, right?
Yeah.
So that would be new EV minus, sorry about that. Maybe I can write once. J dash plus 1, J dash minus B double dash, J double dash plus 1, J double dash. So if I have to do it in terms of J, so my J dash is going to be J dash going to be J double minus 1. So, J, it's going to be J prime, because see, J double prime minus 1 plus 1. So only J double prime will survive. And this is J double prime minus 1. So now let us break it down. So if we want a symmetrical relationship between all the equations, then in one case we have to take J prime, and in other case we have to take J double prime.
Okay.
And then let us take common your J prime square. So B dash minus
B
B
double
double
dash.
dash, and then we also have J dash. And suppose we are, if the previous one was all plus,
Yes.
so let us take also B dash plus B
Plus.
double dash, then it would have been minus, right? Yes. So what is the common equation we got for PQ? So new bar PQ, we got new E comma V plus, this is same, B dash minus B double dash J double dash square, right? And
Yes.
then we have plus. So for P we have minus, for Q we have plus. So
Yes.
let us minus plus. Let us do B dash plus B double dash J prime, and your J prime could be, now your J prime could be what?
It
J,
can take 0, 1, 2 words.
if it now, no, not again. J
No,
prime
no,
will
no,
only
no.
have 1, 2, 3. Yeah,
Yes, yes, one,
because
two,
then
three.
again, yes,
Yes, yes,
J
1, 2.
prime can 1, 2, 3. Then your J dash, if it is 0, then your again J dash is negative. So
Yes.
you have to take it like this. And Sarah has shown some diagrams, right? 48 diagrams, something like that. But we'll only discuss one thing, that suppose that 40 diagram what Sarah has shown for PQR only for the, I think the R band. So oh, I'm making a mistake here. This should be R, right? P R, right? It should be R. So only for the
Yes.
R band you have seen that it has gone and then it has come back, right? Something like that. What Sarah has shown. Let me, I can show you one. I think there is a question from a question in the assignment, right? So so there is a question was something like band origin and band head. So your band origin is 0 to 0, right? So that you will have the idea from here. This is your
Yes.
band origin. In your spectra, you are never going to get this because you are going to have some uh, value of j double prime and this. So you are not going to see actually your band origin there. So this is your band origin. Let me write it maybe. And you plot the photodiodes such as their x-axis is energy. Okay, your x-axis is energy and y-axis is that j or j prime. X-axis is energy and y-axis is your j prime or j double prime, right? And what is band height? Maybe I can write the equation once more. Suppose only for the R branch, you are going to get something like EV, or this is your band height, a band origin, and then you have your P dash. Suppose this is, I'm not separating those yet, J plus minus B double dash J double prime. This is the overall equation. This is your band origin 0 to 0. And when you take, so what happens in our, but in x axis, it is your energy or new bar, right? New bar minus new EV that you can give it a try. And this is your J prime or J double prime. You have seen something like this. And you also have to remember that this is not a continuous line, right? Again, so these are uh, some values of, so it might not be like that this value where it is turning, that is a particular j associated with a j particular value, huh? It could be something decimal also, because this is not a continuous uh, graph. We have remember the population curve for the rotational energy, right? In there it was something like that. And so J max you used to get some decimal value. The whatever integer it is close to, we used to write that. Anyway,
Yes.
so your d mu r by, suppose your d um, j prime maybe. Let us take one. So this is your constant band origin. So it is going to be 0. And then what else you are going to get? B dash to J dash, J dash square to J dash, right? From here.
Yes. Plus
And
one. Plus one.
plus 1, will it be there? Yes, plus 1. right? And here what you are going to get, and J double dash or J dash, those are all also going to be something like, what do you think? I think I'm writing it a little wrong. Maybe for R branch, what we have written here, for R new AV B dash minus B. Let us write it like that. Let us not generalize, because for others it the band head doesn't exist. Double prime. Uh, acha. For R it was J dash, right? For R it was J dash square, and then it was plus B prime plus B double prime, and it was again J prime, right? So what are we going to get from here? We are going to get B dash B double dash 2J dash plus this as it is. So your, and at this point, so this is an inflection. So at this point your slope is zero. So this is again zero, right? Zero equals to your B prime minus B double prime 2J dash plus B dash plus B double dash. So your, and this is your J double dash is your band head. So your 2J band head is actually your B prime minus B double prime divided by plus. You have to take a minus, then B dash minus B double dash. In other way, we can write, I can take this 2 there and minus inside. So 2 B double prime minus B prime. I hope this makes sense. So this is the position of your band head. So we are going to use this equation in the assignment 10 problem, one of the assignment 10 problem. Okay, now with that, this was the discussion regarding the symmetry, sorry, the rotational fine spectra. And only this you can see the rotational fine spectra when your spectrophotometry resolution is very, very good, right? Because for electronic spectroscopy, you don't need that high resolution. You only have to look at the in some nanometer resolution, right? So
Yeah.
mostly it is not visible, most spectrophotometers, and that is not required also. But in some laser based spectrophotometers, these features might be available. Now let us go to the, maybe I can take one more blank page here, maybe two. Okay. So in this case, we are going, and let me check if the recording is going on. Yes, the recording is going on. It's good. Now let us discuss about the symmetry of electronic states. Here, Professor Datta has discussed some of the rules, right? So what are those rules? Can you remember? I will just write down the condition and you can give me the rule. Huh? So, as always, your TMI is something like that. Your total wave function is going to be, sorry about that. Your total wave function psi is multi product of different orbital molecular orbitals, like phi 1, phi 2, phi 3, and so on. And so the character, so the your character, you can say, is going to be a product of all those molecular orbitals, and eventually lead you to, sorry about, I've written Q. That is going to give you your state, how we are going to generate what. So we have to know the electronic configuration first, and from the electronic configuration we are going to generate what is going to be the state of my electronic state, symmetry of the electronic state. And before that also we have to know about the how many so obviously electronic configuration and the point group of that molecule, right? These two are the important thing. So first tell me if my all of the MOs, molecular orbitals, are doubly occupied. So all the molecular orbitals are doubly occupied. First of all, let me. So these are only the orbitally allowed thing we are discussing. Huh? Psi electronic dash, mu electronic, psi electronic double dash, right? And that too, you already know this is going to be XYZ, right? So this is your,
Excited.
yes. So if all the MOs are doubly occupied, so MOs talk about the spatial part, right? So here we are only talking about the spatial part. So again, to become this TMI to be orbitally allowed, this TMI has to be the integrand has to be symmetric. So
Okay.
this triple product has to be symmetric. So first of all, this, suppose all the MOs are doubly occupied. So then what is going to be the state of my and this is the state in the ground state, and this is the excited state, right? So the transition will be allowed when the this triple product is going to be symmetric of the integrand. Now suppose all the MOs are doubly occupied, then what is going to happen? What is going to be the state of my molecule? Can you guess? Let me give you the example of H2. Okay,
Okay.
H2. What is the electronic configuration? 1s2. Sorry, sigma 1s2,
Yes.
right?
Yes.
And 1s we can write it in terms of G, right?
Mm.
I think G plus, right? So these two orbitals are uh, uh, filled, right? So these MOs is filled. What about He2? It is going to
Honestly,
have sigma G plus 2 and then sigma
mm,
U
uh,
plus 2, or what? Can you remember? So plus is going to be dependent on, so this is going to be plus minus, this is the molecular orbital, right? And we are dealing with d sigma h. If we are dealing with homonuclear diatomic molecule, then we are dealing with d infinity h, sorry. And d
yes.
infinity h, if we apply the, let us go to, maybe this is one of the d infinity h, right? So if we are going to change the atoms like the C prime 2, and it is going to be antisymmetric. So, so it is G, but antisymmetric with respect to the change in the position. So it is going to be minus. You can see here also sigma G minus. and this will also be G. So it is like that. So this is my electronic configuration. In case of electronic configuration, I'm writing sigma as a small letter. Now for state, what is going to be the state? Can you tell me? Both the electrons are filled up, right?
Okay.
Then
Capital
what is
sigma.
going to happen? So sigma G plus into sigma G plus, right?
Yes.
And that is eventually give me sigma plus G, right? G into G is G. Sigma into
Yes.
sigma is going to give me sigma, one dimensional, and plus plus, right? What about helium 2 plus? All the MOs are filled.
Yes.
There are two MOs. This is your sigma G minus and this is your sigma G plus, right? All your MO are filled up. Then what is going to happen? What we are actually doing? We are doing that we are multiplying the symmetry of the orbital and to get the electronic state. So if you multiply the same thing with the same thing, that is going to eventually lead to have a totally symmetric configuration, right? A totally symmetric state. So your state, this is going to have your, either it will be totally symmetric or it will contain totally symmetric. So when they are one dimensional, then they are going to be totally symmetric, and when they contain, and when both of them are suppose in some point group, suppose both of them are two-dimensional or three-dimensional, if you multiply the same state, same not the same state but the same orbital, direct product of them, they will lead to, either they will contain the totally symmetric representation. And if my totally, so that's why, if when my orbitals are filled up, so I don't bother about thinking of them, right? I have to think about which of the orbitals are not filled up. So that is going to be my concern, that is going to contribute, or that is going to decide what my electronic state is going to be, right? So this is in, suppose this is H2, this is in its ground state, right? This is helium 2 in its ground state. So this is the ground state geometry is, or ground state electronic state is totally symmetric, or A1, not A1G, here it is sigma G plus, right? Now suppose, now the second condition, maybe I can write it in a different color. Okay. The second condition is, suppose all except one MO is, or are W occupied. What does that mean? That all the MOs are W occupied. Now you have, suppose your H2 plus. Okay. So your H2 plus is what? Sigma G plus 1. What
Yes.
about He2 plus? That is going to be your sigma G plus 2, but sigma G minus
Minus.
1. So these orbital have only one electron, but this is filled up. So I don't bother about it, right?
Okay.
So this I have to, this is going to contribute to my electronic state, and that electronic state is going to be, if there is only one electron, right? So that is going to lead to me that the symmetry of the state is going to be state is going to be symmetry of the unoccupied MO. Do you understand?
Yeah, trying to understand, sir.
Okay. So
Now, this thing I can understand.
this thing you can understand, right? Okay.
Yes.
Now, then if we can understand this, now let us go to the next step. Next one, huh? Next condition. That suppose two electrons are in two non-degenerate MOs. Like suppose a excited state. Huh? Suppose here let me start with this color 3. That two electrons are in two non-degenerate MOs. Suppose this is how can I say? Maybe what can I take? O2 minus. O2 minus. Okay. What is the electronic configuration of O2? O2 is all are filled. Then there is 1 pi u orbitals. They have 4. Okay. Then they have the antibonding orbitals, pi orbital, that is going to 1 pi g. Okay. They are filled, not filled, half filled. And suppose I am adding one more to the next one. What is going to be the next one? Pi g, I think sigma. And that is going to be the sigma anti-bonding to sigma u. So I am not sure what is going to be the nomenclature, 1 or something like that. I think not 1, 3 or 4, but I'm not writing it. Sigma u, suppose. Sigma u and some one electron is there. Okay, this is O2 minus. So one electron is there. Oh, I am writing it wrong. I'm very sorry. This is not a proper example, I guess. Maybe I have to choose something else, not O2 minus. But suppose I think you can understand my point, what I'm trying to say. Maybe I can draw it something like this. Do not think about any atom. Suppose these are the MOs. Okay. So in ground state, it was like two are like this in ground state. And suppose in excited state, it has become one electron has gone to this. So I am specifically not denoting the spins for other purpose. Huh? And let us think of them like this. We don't know what spin they are. Huh? So they could be either same spin or different spin. But let us not think about that. Suppose this is in ground state and then some photo excitation has happened and it has gone to the excited state. Okay. Now these are two non-degenerate MOs and there are two unpaired electrons. So what is going to be the symmetry of this state? Can you tell me? What do you think? Or is it going to be a direct product?
It must be dying product.
So direct product that we are agreeing on. Direct product of
These two symmetry of these two.
yes, two unoccupied demos, right? Unoccupied, a non-degenerate demos. So we now we are convinced that we need to take we have to do a in most of the cases we have to do a direct product of the unoccupied demos. But what if the two electrons reside in the degenerate MO? For example, your O2 that has this field orbital, right? So this is the electronic configuration. So they have something like this. We don't have to think about pi u, right? Fully filled. So they are
Fully.
up to this much. The product is totally symmetric. So I am not worried about that. So we have to think of this case 1 pi g 2. So this is not 4. So they are according to Hund's rule. Is it Hund's rule or Aubau principle?
Four
Uh,
principle. No.
uh,
Once.
I think Hund's rule.
Yeah.
So they are like this. So they are unoccupied into pi
Mm.
g. So this is 1 pi g and this is 1 pi g. So what is going to be my state in this case? Obviously direct product of them, right?
Yeah.
Symmetry of the state going to be the direct product of the unoccupied MOs,
Mm.
but they are restricted by Pauli exclusion principle, right?
Mm.
Because now as they are degenerate, so they cannot be anything. So what are my options? How many situation we can get? Two electrons and or two. So total number of space are four, right? Here
Yeah.
it can be two. Here it can be two, right?
Yeah.
There are four spaces and two
Mm.
electrons. So
Mm.
how many ways they can uh, actually fill up? So maybe let us write it here. Symmetry of electronic state of oxygen, and we have the electronic configuration. I will just write it once more like this, and we have two pi g's, right? And we have 4c2 is equal to 6 ways to fill the four boxes, right?
Mm.
Each pi, and we have only one electron. Now we can do it in six ways, and but the direct product, what does that tell us? So this is your pi g,
Yeah.
small pi g into small pi g, but it will lead to me what? Pi g into pi g. So that is going to give me here 4 cos square phi, right?
Yes.
Then here it is 0, again plus 4, then 4 cos square phi again, then here it is 0, right? Something like this.
Yeah.
And by induction process, you means for here you can't. So this is your reducible representation, right? So
Yeah.
this direct product is not a irreducible representation. So this is a irreducible representation because you can see the dimension of your identity operation is 4. But you can see in the character table there are no such dimension. Fourth order dimension is not there. Only first order and second order dimensions are there. Right? Not
Yeah.
first order, second order. I will say 1D and 2D dimensions are there. Irreducible representation. So this must be a reducible representation which will contain the your
I-
no, not so which will contain some irreducible representation, and we need to figure them out. And
Yes.
by induction method, I will not go into deep as Sir has already discussed this, but you can
Yes.
take help that G into G will always going to lead you G. So you need to take only those Girard ones only. You don't have to think about the this below part. So only the Girard ones will work. So that is you will see that this is eventually if we don't have the product table here for this character table, and you can't really use that our shortcut method of that 1 by h into character of your reducible representation into the your character of the symmetry operations character table a character, because your h is infinity here, right?
Yes.
So you we
Yes.
can't use that formula, so you have to go with some induction formula, and we'll see that this is going to lead to us uh, actually sigma g plus sigma g minus and one more, that is your delta g. Suppose your electronic states, sorry, suppose your orbitals were non-degenerate, like this third condition, like this third condition. If it was non-degenerate, then what are the options? So then it would have been either singlet sigma g plus or triplet, because there are two electrons only. So two
Yes.
electrons will always have either singlet or triplet. They can't have the doublet, right?
Yes. Yes. Yes.
So if there are two electrons, then it has to be singlet or triplet. If there is only one electron, then it can be doublet, right?
Yes.
So
Double. Yes. That's one.
now in these cases where we are discussing about two electrons, they can have these kind of symmetries, singlet or triplet sigma g minus. So we don't say one sigma g, we say singlet sigma g. So that is one convention what I'm trying to do. So it could be either singlet delta g or triplet delta g, right?
Yes.
And if that was the case, then how many total number of electronic states we are getting for this total, for all of this? Can you sum them up? Singlet
Total.
means only one state. Triplet
One.
means three
One.
electronic states are there. Huh?
Yes. Yes.
Because there are three spin states, right? So three states. So four from here, eight,
Yes. 12.
two from delta
Yes.
singlet delta G, so 10, and six
16.
from, so 16. Total
6.
16 states. But that is not possible, right? Because we
Yes.
already see there are only six
Yes.
possibilities there. So
Yes.
then again, as I told, when you are working in the degenerate state, you have to look at the Pauli exclusion principle, right? And what does
Yes.
that say us? That all the electrons cannot. First of all, Pauli's exclusion principle is came from a sixth postulate of the quantum mechanics, that your total wave function, that is your product of psi space spatial part and psi spin part, that has to be antisymmetric. So if your spin space part is symmetric, your spin part has to be antisymmetric. And that is only one option. You will see that is a singlet condition. And for your triplet condition, your psi spatial is, you will see that is your antisymmetric, and your psi spin is symmetric. That you, in case of symmetric spin, you have alpha 1, beta 1, alpha 1, alpha 2,
Beta
beta
1,
1,
beta 2,
beta 2,
alpha
alpha
1, beta 2,
1, beta 2 plus alpha
beta
2,
1.
beta 1. So your triplet case is your spin is symmetric. Anyway, so you have to follow this sixth quantum mechanical postulate, And that actually leads to the Pauli exclusion principle, to be honest, that no electrons in the same orbital is going to have all the four same quantum numbers, right?
Yes.
So that is going to be the actually what Pauli exclusion principle says, but that is actually originated from this sixth postulate that total wave function has to be antisymmetric. Now you see sigma g plus. So that is this. This is totally symmetric, right?
Yes.
So this
Yes.
actually gives us the special part, right?
Yes.
So my mistake here has to be plus. So so this is your symmetric.
Yes.
Can you tell me if sigma g minus is symmetric or antisymmetric?
G is for symmetry.
G is for inversion, but
Inversion
you have to
symmetry.
look at those symmetry operation where your
Mm. It is
a-
symmetry with respect to yes,
yes
inversion.
atoms are going to change their position or the basis set is going to change their position, like C2 dash, okay, or sigma V dash. There is a mirror plane, so your atoms or your basis set is going to change their place, and based on that you are going to decide if it is symmetric or antisymmetric. Okay,
Yes.
so based on that you will see this is antisymmetric special part. Okay,
Okay.
what about delta G? Let us not discuss for now, because delta G, if you see, you are going to see sigma V is zero. It is a two-dimensional, so we can't
Yes.
really say that if it is it is not annihilating. It is just that it is there in the off diagonal. The character is so the those are there in the off diagonal state. They are not contributing to the character of your for this symmetry species. Okay, so that is going to be very hard to determine, but let us first determine for this one-dimensional symmetry species. Now we know for the first case, our special part is symmetry, right? So my
Yes.
spin part has to be antisymmetric.
Yes.
And what is the only possibility? Can you tell me upon this? Which singlet or triplet? Which one is antisymmetric? If my spatial part is symmetric, then my spin part has to be antisymmetric.
Yes.
So I told you earlier that your singlet state is alpha 1 beta 2
Minus
minus
beta one,
alpha 2
alpha
beta
beta
1.
beta
And obviously there are some normalization condition 1 by root 2.
root two.
That is your singlet.
Yes.
And triplet spin state are
Alpha
alpha
one, alpha
1
two,
alpha
alpha
2
two,
beta 1
beta
beta
one.
2 and alpha 1 beta 2 plus alpha 2 beta 1, right?
Yes.
So they are all symmetric spin state, but singlet is antisymmetric. So your if your spatial part is symmetric, then your total wave function to be antisymmetric, your spin part has to be antisymmetric.
Yes.
Now can you tell me that what is going to be the one that is going to the valid singlet sigma g plus or triplet sigma g plus? Sigma g plus is symmetric.
Yes.
So your spin state has to be antisymmetric.
And here
So will it be
minus
singlet or triplet?
singlet is symmetric. No, that singlet sigma g plus is symmetric, so it will be two. triple.
No, no, singlet sigma g plus is not symmetric. Your sigma g plus is symmetric.
Okay.
That is your special part.
Yes.
Your spin part is your here at your this is your spin part.
Yes.
So your space part is symmetric.
Yes.
So your total wave function has to be antisymmetric.
Yeah.
So if that is the case, total wave function is antisymmetric and your spatial part is symmetric, then your spin part is what?
Spin path must be antisymmetric, singlet.
Antisymmetric. So it has to be singlet or triplet. You are correct. You are saying the correct thing earlier.
Sing.
Singlet. Why there is a confusion? Can you tell me? I think you are having some confusion there.
That
You are
must
saying
be
that
singlet.
yes, that is going to be the singlet state. Now
Yes.
suppose in the case of sigma g minus, so my spatial part is antisymmetric.
Yes.
Okay. So
Okay.
what is going to be my spin part?
The triplet will be there.
So
No,
triplet will be
no. Your space part is antisymmetric. No, no. Then your you will be
spin part will be symmetric.
yes. The triplet part will be yes.
Triplet part would be there, right? So this one. So you already have 1 plus 3, 4 state. So only this is going to be the possible one, right?
Okay.
So your actually your pi g into pi g that led to many state, but for oxygen it is specifically singlet sigma g plus triplet sigma g minus plus singlet delta g singlet delta g. Okay. Can you now tell me the relative energy order of them? Which one is going to be have the highest energy? Which electronic states? According to Hund's rule,
Mm.
multiplicity.
Multiplicity has the
So
lowest energy.
lowest energy. So the triplet sigma g minus is going to be have the lowest
Okay.
energy, and
Then
then both are singlet.
yes.
Then what will happen? The one with the more degenerate state that is going to be the next lowest
Next
energy.
low.
So that is delta G,
Delta
singlet
G.
delta
Yes.
G. So your energy states will look like you 1, 2, 3. Your third one is triplet delta G minus singlet delta G, and this is the energy scale, and this is your singlet delta G plus. Now based on this, as you remember, these singlet oxygen generation. So there is huge number of papers are now publications are now taking place on how to generate singlet oxygen or how to reduce the or how to block the pathway of singlet oxygen generation, right? I hope you have seen there are papers or a number of papers in every day. There papers are publishing about singlet oxygen generation and other things. So actually, singlet oxygen generation is not good for your health or something like that. As I think Sir has already discussed the porphyria or those kind of positions. Actually, depending on this energy gap, I think you have already in the class Sir has told that what is going to be the color of your liquid oxygen, and that color
Mm.
is actually blue in color because the the color that is absorbed, that is red, and the green part because that has the so it is something like 13,000, I don't remember the exact value, 13,000 centimeter inverse, and this is something like 7,000 centimeter inverse. You can see these are actually spin forbidden processes, triplet to singlet,
Mhm.
right? But still they are allowed by those the spin forbidden, but very, if some way they can be allowed, like spin orbit coupling, right? So
Yes.
in that cases, like in liquid oxygen, they are in so in comparison to gaseous phase, liquid oxygen has more number of oxygen molecules, right?
Yes. Yes.
So they are more close to each other, and that's why in liquid oxygen you can see that it can absorb that part of the light, and only blue light is being emitted. So your actually liquid oxygen, very, I think at very low temperature it can be produced. If you pass the oxygen gas, it will become liquid oxygen, and that will look like a blue liquid, and that is very much um, flammable. It can blast. I think sir has given an example also in our just the lab in front of us. They are doing some cryogenic experiment in presence of oxygen, and
Yes.
the
Yes.
student have seen some blue liquid. And
Yes.
he or she might have thought that, oh my god, what is this? This was not supposed to be there. Is this some kind of impurity or something like that? I think he or she has tried to look uh, from closer distance, and it blast that time. So,
Yes.
so that is one more thing. So and this singlet oxygen generation is important in terms of the photodynamic therapy and all. If you can, uh, so photosensitizes porphyrin kind of molecule, if you can directly place that thing into, means sensitive to you, selective to your tumor cells, if you can directly send that photosensitizer to your tumor cell, and you can irradiate that, then that
Yes.
photosensitizer will actually going to annihilate this singlet oxygen generation. Oh, sorry, that is going to generate the singlet oxygen, which is toxic for the cell, and that singlet oxygen is going to kill your tumor cell. So that is also some that is known as actually photodynamic therapy. So those porphyrin kind of or phthalocyanine kind of molecule, they are known for photosensitizing. So what they actually do, they actually get excited, and from their excited state, they actually he transfer the he transfer the so their singlet oxygen to, singlet electrons to their triplet states photosensitizers, and two of the photosensitizers actually they then in the triplet state they can actually interact with oxygen, and that energy of the oxygen, two triplet oxygen can electron can be promoted to your one of the means they can, the energy can add up converted to the singlet oxygen, and that can form singlet oxygen. I think that part has been well taught by Datta sir. I think if you have any further doubt we can discuss, but this is the electronic state of the oxygen, and mostly in the ground state we say the ground state is triplet, right? Most of the cases for the oxygen. For the most of the other molecules, it is singlet. But oxygen is one of the prominent molecule where the ground state is actually triplet. So most of the electrons are there in the triplet, and as the other transitions are forbidden, that doesn't really takes place. But it takes place otherwise, like spin orbit coupling, but the intensity would be very less. Okay. Now maybe we can go to the case of benzene, right? Electronic state of benzene. And so, are you able to grasp the material what I'm saying here?
I'm trying to grab. So it's very difficult for me, but I'm trying, sir.
Okay. Did you attend the lectures?
Yes, yes, but that was very fast. That was actually carried out in very fast pace.
Okay, okay. Maybe
Yes.
I can go a little slower then also. We can talk about the assignment problem later, but to this thing can we can clear it right now if you have any doubt. So, do you want to discuss something from here? What might look like a confusing part to you? Electronic states, how to determine the electronic states?
This thing I understand this thing.
Okay, now then let us go to the benzene. This is B6H point group, right?
Yes.
So this character table is also there, and this is the product table. So in case of benzene, so we'll again start from the basic that we have to look at the electronic configuration. And for benzene, if you remember the electronic state, we have to only discuss about the pi electronic state. We don't have to think about the singlet state. Those are all filled. So the here the pi electrons we have to think about. And I'm not. Maybe I can draw. So pi orbital. The first pi orbital looks like this. All of them are all the pz orbital. Z is along the plane. Z is coming towards us. So we are actually drawing this. Okay, we are looking from the top. So we are only looking at like this. So this is one. Then this is the pz orbital. Then this could be there. This pz orbital. All six pz orbitals are there here, and here three of them are of different phase. And here the orbitals are a little different. So the here there are non-bonding. Okay, so these are the homos. Okay, highest occupied molecular orbital, these two. This is filled. So benzene, 6 pi electrons are there. If I draw it like that, maybe in between the here, they are all filled up in the ground state. Because of the space constant, I am drawing it like this. And whenever you draw a molecular orbital diagram, you should always mention this is your energy scale. Okay, and don't worry, I am drawing this by looking at some note. So you don't have to mark this thing. Just for the sake of the discussion, I'm drawing. You don't have to remember all of this. So these are HOMO, highest occupied molecular orbitals, and these are lowest unoccupied molecular orbitals, LUMO. So there is a way how you can say hey, that energy of these, which of these are at what position. See, here in this orbital, you can't, can you see any nodes for the lowest energy orbital, molecular orbital?
No,
No nodes, right?
I would say.
So that tells us it has no nodes. Now, can you go to here? How many nodes are here?
We are in out of phase, so three nodes.
No, no three nodes. See, nodes is only here, a nodal plane.
Okay, only in between. Yeah, okay, okay.
Hmm? Now, how many nodes are here in the this part? One, two, one
Yes.
plane, two plane, right?
Okay.
Can you see
Okay.
two planes?
Yes, yes.
So let me draw it. You can see there are two nodes associated with this. So here you saw one node, here you see two nodes. Now tell me how many nodes are here on the
Uh,
top?
on the top,
One,
in one, two, then again, yes,
one, then
there is
two,
also no, yes.
and then I guess three, something like that. Let me draw it here. First, let me draw with the two nodes. So one node is here, right?
Yes, yes,
And then another node is here.
yes,
Another node is here, and another. So this is actually one node, and this is
yes,
actually one node, right?
yes.
So this has two nodes, nodal planes. Now what about the top one?
I think three is
It is going to have three nodes, right?
yes.
So that is in you have seen in many quantum mechanical system that if the number of node increases, the energy of the state actually or the orbital has increased, right? Similarly, here as you have three nodes, so energy of the state is maximum. So that's why. So this is a something like this has the highest energy. But let, I also forgot that what is going to be the electronic states or the orbital cell looks like. So this is actually your A2U. This is E1G because they both of them belongs to the same symmetry species. And then this is E2U and the fourth one is B2G. Okay.
Okay.
So as you can see, and your electronic states are in ground state, electronic configuration. Can you tell me the electronic configuration? A2U has two electrons. E1G has four electrons, right?
Yes.
So what is going to be the symmetry of the state?
So it will be U into G. U will be
Sy-
there.
Symmetry will be
U.
E. So E1G is there. So what I told you that if I multiply this, I am going to get the same thing. If I am going to multiply the same orbital, then I am going to get A1G as a. Obviously, I am going to get some A1G, right? Totally symmetric representation, right? If I multiply the same thing, what about excited state? Now the electronic configuration is going to be A2U2, E1G3, E2U1, right?
Yes.
And now what is going to be the symmetry of the state? Can you tell me? Direct product, right?
Entire
Direct product of
these three.
these three. Which three?
No, no. To A2 is not required because it is already full filled. So it is
Okay,
not required.
so I am not bothered about that. What
Only
else?
E1G, only E1G and E2 you.
So suppose one of the electron has been promoted to there,
Yes.
any one of them. So
Yes.
one of the orbital is full, filled.
Yes.
So I also don't have to think about that also.
Yes.
So I have to take only one of the UNG
And E to
and
you.
E2U.
Yes.
And see, E1G, where is E1G? E1G goes like this and E2U goes like this. So this is my product, right?
Yes.
This one. Let me highlight, maybe I can highlight E1G and E2U. And first of all, G into U. So all is going to be U, right? So B1U plus B2U plus
E1.
E1U. So now tell me, is there any, so now in this case, as you can see, we are dealing with two non-degenerate states, right? Two non-degenerate homo
Yes.
E2, E1G and E2U molecular orbitals are not non-degenerate. So we don't
Yes.
really bother about so the spins are not interconnected.
Yes.
So in ground state, it is A1G capital. In excited state, it is actually can be singlet B1U plus singlet B2U, and obviously it is also singlet, as you can see, right? All these spins are paired up in the ground
Yes.
state, and it can be another triplet B1U plus triplet B2U plus triplet E1U, right?
Yes.
Now, the only spin allowed transition is
Singlet to singlet.
1A1G, singlet A1G to these three, either of these three, right?
Yes.
So, so that is your one is singlet A1G, your XYZ, right?
Yes.
And one B1U, one B2U, or
One.
one E1, E2U, or E1U, sorry, right?
Yes.
So now we have to take, so this is A1G, right? So I don't have to bother about this. So my transition will be again will be in transition moment integral will be non-zero when the product of the
Yes.
final
Symmetric.
state
Yes.
is
And
go,
symmetric with the experiment.
no, the is symmetric, but the final state should have the same symmetry that of your
XY.
XYZ.
Yes.
Now your X has a XY, they have this E1U,
Yes.
and Z has A2U, right?
Yes. Yes.
XY and Z is this. So you see B1U. So let me write it here also. So in one case you have singlet B1U, A2U, or E2U, E1U, This is for your 1A1G to 1B1U. Then we have whatever I am writing. Do you have any doubt?
Not really clear to me that is.
These are my excited states, right? Singlet excited
Yes,
states.
yes,
So I'm trying to see that which one is going to fetch me a symmetric triple product. Now let us start from A1G to B1U. Huh?
yes.
So A1G, so I am not bothered about this. Let us not think about this. When I multiply B1U with A2U,
Yes.
see B1U, B1U with B1U with
E2,
A2U,
A2.
that give me B2G. Okay,
Yes.
and when B1U I multiply it with E1U, that give me E2G.
Yes.
So they doesn't yield any totally symmetric representation, right?
Yes.
So it is, so sorry that, where am I? So this is spin allowed but orbitally forbidden, right?
Yes.
Because the first one is B2G and another one is E2G, the
E2.
product, right? I'm
Mm.
writing. Now let us think about B2U A1G. Sorry, B2 A1G I am not bothered about. B2U
Mm.
and A2U. B2U and A2U. This one.
E1.
B1G
Yes.
and E2G. So B1G and E2G. Again, no totally symmetric part, right? So spin
Yes.
allowed, orbitally forbidden, right? Now
Yes.
one E1U, again I am not bothered about this. E1U and A2U,
E1G.
E1G and a sum of these.
Yes.
And that sum actually contains
E1G.
A1G. So one is E1G and another give me A1G plus A2G plus E2G. So that makes spin allowed and orbitally allowed, right?
Yes.
So that is going to have the highest intensity absorption peak, that is going to absorb more, right?
Yes. Yes.
Okay, that is one thing. Now next what? Next is, let me check what is next. Next is that, so these states These we know this is going to have the highest intensity. This is your spin allowed and orbitally allowed. But what about these? Spin allowed but orbitally forbidden. So what can come as a savior? Spin orbit coupling.
String.
Sorry, not the spin orbit coupling, but your
My
vibronic coupling. And we can go back to the first slide we had today. This one, right? So in this case, your this product, so they are now coupled. So
Yes.
this product has to be symmetric.
Yes.
And now let us go back there. Maybe I can. Okay. No, I don't have them. So what I will do is I'll copy paste them. Can I cannot erase them. But maybe I can. Here what I will do. So this is what we are discussing, right? That this is fully allowed, this is orbitally forbidden, and this is also orbitally forbidden.
Yes.
Now it can only be vibronically allowed. So when now let us just come here. So this is your psi electronic, this is your mu electronic, right? And this
Yes.
is your psi electronic double dash. What else is going to be there? Your psi v dash, psi v double dash, and your mu v, or your
Yes.
overall mu, right?
Yes.
That is also your that is now inseparable for spin orbit, sorry, vibronic coupling. But you can see that we have already got psi electronic dash, your mu dash, and psi electronic double prime. And we know your vibrational transition is going to take place from 0 to 1. Why? Your 0 has the maximum uh, population, right?
Yes.
And it can go to 1, 2, 3 anywhere, right?
Yes. Yes.
So maybe I can write 1 dash 2 dash 3 dash 0 dash 2. So psi v 0 dash, you already know that is also A1G. The symmetry of this psi v 0, because
Yes.
it is a constant, right?
Mm. Mm.
So there are no Hermite polynomial. But psi v dash will have the symmetry of xi.
Yes.
It will depend on the not the xi, but it will depend on the Hermite polynomial. Mostly it is 1 dash, right?
Yes. Yes.
So we have to look at the normal modes of vibration. So you see your normal modes of vibration should have this symmetry,
Yes.
because we already know this part.
Mm.
This part has led to either of these, right? And
Yes.
only remaining is the symmetry of psi v dash. So that symmetry species has to be either of them, so that
Mm.
I will get a
They
totally symmetric representation,
all day. Yes.
right? So their symmetry has to be equal, symmetry
Mm.
of these and symmetry of the other products. So that, and similarly for these also, the in this case,
You want
symmetry
detail.
of the normal mode
Yes.
of the excited state has to be either B1G or E2G, And that is what written here. That vibronically allowed, let me use the laser pointer. So vibronically allowed by B2G and E2G vibrations. And this 1B2U, that is vibronically allowed by B1G and E2G vibration.
Yes.
So do you get this point?
Yes. Yes.
Okay. Now next is the absorption spectrum of benzene, and the obvious thing is that the y-axis is in log so that we can see the higher intense and lower intense peak also. Now the max highest intense peak is absorption peak is this one, right? And what could be it due to? Both spin allowed and orbitally allowed,
Yes.
and that is what? That is your A1G to E1U,
Even yes.
fully allowed.
That's fully allowed. That is fully allowed. Yes.
So so that's what it is. This is fully allowed. Now these two, as you can, this peak and this peak, they are not fully allowed. They are spin allowed but orbitally disallowed. So some vibronic coupling is required. This one and this one, and you can see there are even smaller peaks there. So they are orbitally not allowed. Even spin also not allowed.
Yes. Okay.
So that's why they are so weak. Only because we have taken a log scale of the absorption of the epsilon, that's why they are even visible. So
Yes.
if you have taken just a linear scale, then they are not even visible.
Yes.
So these two, these two shoulder band like thing, these are two spin allowed but orbitally disallowed. So even though as we can see them, so there is some vibronic coupling is taking place. Now let us focus on to that benzenoid band. So this band around 250. Any
Yes.
molecule that has benzene group or phenyl group, that will show this benzenoid band. Okay. So
Okay.
that band, so that is written. A closer look at the benzenoid band. So from here, what you can see is that there are multiple peaks. Okay.
Yes.
Now the rate shifted peak among those
Yes.
is, so rate shifted means the energy is lowest.
Lower. Yes.
So that is only can be possible for 0 to 1 dash,
Yes.
right? Because
Yes.
0 is the at room temperature, the only populated state is the new 0, V0.
Yes. Yes.
So the least intense, least energy transition would be 0 to 1 dash.
Yes.
Other would be 0 to 2 dash, 0 to 3 dash. The energy will increase, and so that your wavelength will be blue shifted. So
Yes.
the rate shifted highly intense peak is 0 to 1 dash. So that is why it is written 0 to 1 dash symmetry. Huh?
Yes.
Else there is even a smaller peak is there, H, hot band. Why they have seen with varying the temperature, this absorption has changed. This has
Mm.
shown at higher temperature. At higher
Yes.
temperature, this vehicles to one band is going to be populated, and from 1 to 0 can be possible now. Delta V is plus minus 1. So V
Yes.
1 to V0. That's why this is hot band. 1 to 0 dash here. Now what from spectral you have the, from the spectra you have the wavelength, so you have the energy also. So that energy for A1, so that is your 0 to 1 dash, 0 to 1 dash, so that is your 0 to 0 plus your vibrational energy in the excited state V dash
Yes.
x, so that is equals to 38,611 centimeter inverse. That has been taken from this peak, A1 peak. Is that part clear?
Yes. Yes. And these multiple peaks are due to this rotational lines, or
Yes,
this
these are due to
again.
rotational. Yes. And these bands A2 is 0 to 2 dash, 0 to 3 dash. Okay.
Yes.
Now this H band is hot band. So 0
Yes.
to 1 sorry, 1 to 0 dash. So that is your E00 minus this
Yes. Yes.
ground
Yes.
state vibrational energy. And for assumption, let us take both of them to be equal. The vibrational energy are equal in the ground state and the excited state. So the gap is equal. And from there you have two unknowns and two equation, and from there you can see. So in band origin you cannot see in the spectra, but from this equation you can guess the position of the band origin. 0 0, right? 0 0 transition. And you can also guess the vibrational gap between 0 to x, that is coming as 564 centimeter units, and that is close to this E to G. and
Yes.
and these symmetries has been collected. Actually there are a lot of normal modes of vibration was there, and upon that only the, as we told, B2G, E2G, B1G and E2G vibration, normal modes of vibration are going to lead to your vibronic coupling, right? And it has been
Yes.
shown that B1G is not there in no normal modes of vibration in the benzene actually have the symmetry of B1G. They have either B2G or E2G, and based on
Yes.
that those are separated. And from there it has been uh, told that this transition, the benzenoid band, is only due to this E2G vibration, and B2G and E2G is this one. Maybe let me show this assignment of bands. Do you have any confusion so far of assigning these bands?
No, it is clear.
Hmm?
Not clear.
It is
That
also
is
clear why they have taken, they have started with the benzenoid band.
yes.
Why?
This is the
Because these features are well visible in the benzenoid bands and not that much visible in the this.
only yes.
Yes, they are actually overlapped by this highly intense
Yes.
fully allowed band A1G singlet 1G to singlet E1U. So that's
Yes.
why it is better to take benzenoid band, assign this, and then whatever is left out, that is your
Yes.
B1U. Okay. And
Yes.
here they have also seen that this phosphorescence, so this is mirror image to the phosphorescence spectrum. Phosphorescence is triplet to singlet, right?
Yes.
As your ground state is singlet, so phosphorescence is singlet, triplet to singlet. So here it is singlet to triplet. So that is another triplet state was there, right? Triplet B1. So triplet B1U, I guess here. So
Only B1. Yes.
I'm not sure how they have assigned it to only triplet B1U. Why not B2U or E1U? But for
Okay.
the moment, we will believe them that it is coming from the triplet singlet A1G to triplet B1U. So is this clear so far?
It is clear.
It is clear, right? So with that, we can go to week 10 assignments. Okay, let us quickly finish this. So first question is that for naphthalene, we have done for benzene. Now they have asked for naphthalene, even more bigger, right? Naphthalene homo to LUMO transition with inversion of spin. So spin is changed. Singlet to triplet has taken place.
Yes.
Homo to LUMO transition. So which
Yes.
one of them is going to correct? So if there is a change in the spin state, inversion of spin,
Yes.
then that is not fully allowed, right? It is spin
Yes.
forbidden.
Simple.
The second option is orbitally allowed but spin forbidden.
Yes.
Then the third option is spin allowed but orbitally forbidden. It is not spin allowed. So
Yes.
first
Yes.
two options are cut, not first two,
Yes.
first and the second, a third. What about orbitally as well as spin forbidden? I don't think if you actually carry out the naphthalene, okay, so maybe you can try it. Did you try it to determine what is the point group of naphthalene and all?
No, no, no. I
Hmm.
uh, I just
Orbitally allowed but spin forbidden, right? Because spin is forbidden, but it is eventually going to be orbitally allowed with almost the same treatment as benzene, but the point group is different, I guess. It is not D6H. But you have to check the point group. I think let us see what is the point group of naphthalene. Let us search D2H. In case of benzene, it is D6H. So
yes.
D2H is, I think, better than D6H in terms of less symmetry operations are
Yes.
there, right? Maybe you
Yes.
can try once. That what is going to be the. Do I have D2H here? No, I don't have the D2H character table. So what you have to do, you have to think about the pi electronic configuration for naphthalene. Naphthalene, how many pi electrons are there? Tell me, 10 or 12
Naphthalene.
naphthalene?
I think 10 is there.
10 electrons.
Yes, 10.
So 10 pi electrons means you have 5 field orbital in the ground state.
Yes.
That is also A1G, right?
Yes.
Singlet A1G. And then you transfer one of them to the higher orbital, LUMO,
Yes.
and now see what is your HOMO and LUMO's electronic state that you have to see. Okay.
Yes.
And then you can actually check for once that what is going to happen, what are the electronic states of the excited state and the ground state, are they really orbitally allowed? You can check once. That would be a, maybe if you check that, then you will be even confident. So maybe we can do that on the next day, or you can try at home yourself, right? Maybe we can try on the next day also. Okay, now the next one, states that cannot arise from the ground state electronic configuration of O2. So from O2, what are the states we have got? Sigma G singlet, triplet sigma G minus, and singlet delta G, right? So
Yes.
this is sigma singlet G that will arise, right?
Yes.
But so, oh, acha. So this is not a correct option. This is a correct option. So these are the two states. So these, whatever I have cut, that are going to generate. In the question they have asked which are not going to arise, right? So these
Yes.
two are not going to arise because of the sixth postulate of the quantum mechanics, or even you can say Pauli's principle. Okay. Now, third, rotational constants. So you remember earlier we have got something J band head.
Yes.
What did we got there?
B1 plus B0 by B1 minus B1 minus
B1
yes. B dash plus B double dash. Yes.
B dash
Dash
minus B
plus
double
B double
dash
plus
divided by
2 into B dash minus B double.
I think the B double dash minus B dash was. Yes.
Yes.
So my in excited B double dash is 10 centimeter inverse and B dash is 9 centimeter. What does that tell me? What is my bond length in the excited state? Is it greater than or less than the ground state?
It is greater than a
Correct.
bond length, na?
Huh?
Yes.
And this is 19 by 2,
2.
right?
Yes.
And
Yes.
you have at band head your now new R is your new EV, your band origin plus B dash minus B double dash J prime square plus J dash. So now when you plot it,
Yes.
then this is given. Actually, this is not your band origin, I guess. This is your band origin is um, no, this is your band origin, right? So
Yes.
that is your 18,753
Minus B.
centimeter inverse.
Yes.
Then B dash minus that is going to be minus 1 centimeter inverse into
Yes.
19 by 2 whole square
Yes.
plus 19
19.
centimeter inverse into 19 by 2.
Okay.
So when you do that, I think you are going to arrive at the fourth option, right? Let us see.
Yeah. Yes.
Uh, 18,753 minus
Minus 19 by 4. 19 into 19 by 4.
hmm, then plus 19 into 19 divided by 2. 18,843.25. That is
Yes.
close
Yes.
to this.
Last
So
one.
this is correct. The fourth one.
Yes.
You can even try with, you can say, how come 19 by 2 is a point? See, the band head is this position. It
Yes.
may not, it is not like it has to be a particular Z dash. It is not continuous. So that's why it
Yes.
is coming as 19 by 2. If you
Mm.
take 8 or if you can, so if you can take 9 or if you can 10, so your
Yes.
9 or 10 might be something like here. So
Yes.
to get this, you have to take 19 by 2.
Yes.
If you would have done it by 9 and 10 and you put 9 here and 10 here, then you might have gone something else, these or these, either three of these. But this is the actual where your this Fortet diagram is actually has zero slope. That is the point you have to consider. Okay. Now next, let us go to the fourth question. Symmetry of the states arising from the configuration of homonuclear diatomic molecule means D infinity H, right?
Yes. Yes. Yes.
Like oxygen, but it's not oxygen because pi U1 and pi G1. So let us go to D infinity one H, this homonuclear diatomic, pi G and pi U, right? Pi U1 and pi G1. So if I multiply that 4, then 2 cos phi, 4 cos square phi again, right? Then I have, I think 0. Then I have minus 4. And then I have
4%.
minus 4 cos square phi, right? Then again I think I am going to have 0 here. Now again this is a reducible representation, but we can't take help from our previous equation. We have to do it by induction method.
Yes, yes,
Obviously G into U into pi G, right?
yes.
So all the things has to be U first,
You are.
right?
Yes.
So let us see pi G into pi U, what it could have been. Um, Only 1 plus 1 plus 2, 1 plus 1 plus delta U, 4, then 4 cos square phi, 4 cos square phi is 2 into
Cos 2 theta minus 1. Mm. Yeah.
2 cos square phi.
Yes.
2 cos square phi is
Cos 2
uh,
theta minus.
cos 2 phi minus 1, something
1.
like that. So
Yes.
2 cos phi minus 2, cos square phi minus 1. No, see, cos 2 phi is cos square phi minus sin square phi.
Okay. Yes.
So if I have to take uh, cos another cos, so sin square phi is 1 minus cos square phi.
Yes.
So that is going to give me, instead of sin square phi, if I write, sorry about that, sin, sorry, 1 plus cos square phi. So 2 cos square phi minus 1. So 2 cos square phi minus 1 is cos 2 phi.
Got.
So 2 cos square phi is 1 plus cos 2 phi. It will be plus.
Okay. Yes.
Okay.
Mm.
Better to remember only this part. Cos 2
Yes.
phi, cos square phi minus sin square phi. From that we can arrive at any of those. So see, if I am taking pi g into pi u, I am now taking this one, that sigma plus u plus sigma minus u plus delta u. Why I have taken it? Because I have already have some idea how the pi
Yes.
g into pi g has evolved.
Yes. Yes.
Now let us see what about this. Minus 1 is minus 2, but what about this? Minus 1,
Minus 2 is minus 4. That is exactly matching.
that is also matching.
Yes.
Then minus 1, so 2 cos phi
Mm.
minus 2. So that is
Mm.
my 2 cos phi minus 2. 2 cos phi minus 2.
That is also 4 cos square phi.
4 cos square phi, is it? So
Yes. In the last, you have circled it, na? 2 cos 2 phi equal to 1 plus
I think I
this.
have I done some, let's say, 4 cos square phi. So this one, right? But wait, this is minus 4 cos square phi. So, oh, I have to take this. I was looking at this. I'm very sorry. 2 cos 2 phi. 2 cos 2 phi, yes, it is right. So it has to be
Yes.
my 2 cos 2 phi minus 2 cos 2 phi minus 2. So this is minus 4 cos square phi. Yes. So that is also matching.
Yeah.
And 1 minus 1 and 0, that is also 0. So that is also matching. So my pi u into pi g lead to
This. Yes.
sigma u, let me sigma, both sigma u plus minus and delta u.
During exam, whether you are going to provide this table,
The
character table.
character table will be provided to you, I guess. I am sure that it will be provided.
Okay.
Else you can't mug up. This is very hard, right?
Yes. Yes.
So see a homonuclear, but both of them are different, right? Pi u and pi g,
Yes.
right? So they can be
Yes.
either, so they can be singlet, or they can even be triplet also. So they doesn't have that stringent here because
Yes.
those are non-degenerate.
Yes.
So, but that so symmetry arising, which will arise sigma u plus, obviously it is going to arise sigma u minus also arised, and also delta u, right? All of these three, right?
Yes.
Okay. Now question number 5. For N2, again homonuclear diatomic molecule d sigma h, d infinity h.
Yes.
So we have uh, N2 1 sigma plus g, singlet sigma g plus to triplet pi g, right?
Yes.
Firstly,
Yes.
this is not fully allowed, spin disallowed, right? Spin forbidden,
Yes.
right?
Yes.
Are they orbitally allowed? That I have to check pi g and sigma g plus, right?
Yes.
So again, let us come back. Pi g is sigma g and pi g, these two, right? So
Yes.
they are related to 2, then 2 cos phi,
Yes.
then how much? 0, then plus 2, then minus 2 cos phi, right?
Yes.
And then 0. What is that? 2, 2 cos phi, 0 plus 2, 2, 2 cos phi, 0 plus 2.
Itself only because it is multiplied by A1G. That is only fully symmetric.
So it is same as this
Yes.
pi
Yes.
g,
Yes.
right?
Yes.
So now you have to look at the symmetry species x, y, z are where, but your symmetry species x, y, and z, they are a1u and e1u. That is not pi g, right?
Yes.
So that
Yes.
is also spin orbitally, also orbitally as well as spin forbidden. If
Both
you
forbidden.
multiply this, you are going to get pi g,
Yes.
but your, so this is your psi final and this is your psi initial, but your xy is pi u
Yes.
and v is a2u. Maybe instead of a2 I should write sigma plus. Are they matching with the answers given in the model answer? I have not checked that. I'm just asking you.
They told they provided that spin allowed but orbitally forbidden. It is not correct.
Yes,
Spin
how come
allowed.
it is spin allowed 1 and 3?
Yes.
Right. So I'll ask them to change the answer. Okay. Now question number 6 for benzene. A1G to B2U transition is orbitally forbidden. It can become vibronically allowed with the involvement of a vibrational normal mode of symmetry. Let us see. One A1G to B1U, B2G and E2G. Right? Oh no,
Yes.
to B2U, to B2U, B2U. B2U is B1G and E2G. B1G and E2G. But unfortunately, only E2G is present, right? B1G is not present as any normal modes of vibration, but that is what it is. The well-known benzenoid band is what? Spin orbitally allowed but spin forbidden.
This that was orbitally forbidden but spin allowed.
Right. So the third one is correct. Right?
Yes.
It was 1 sigma g plus 2, 1. Sorry about that. Spin allowed, that means it is like this. And this, let me check what it was. E1U. Right? No, not E1U. B, B2U. Right? 1A1G to 1B2U.
Yes.
Okay. So with that, uh, we can actually means we have finished this. So assignments are done. So maybe we'll meet on the next day and we'll discuss the naphthalene problem and the NMR problems, right?
Yes. Yes. Yes.
And with that, I think that would be our last session. So we'll meet on the next Monday then.
Yes. Yes.
Till
Sir,
then, yes, yes.
till now I have not received this admit card. So can you please tell me when the admit card is released? Going to
Uh,
release?
I am actually not sure about that. I think so. You have paid for the registration fees and all, right?
Yes. 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 I have already paid
Uh,
and registered for this exam.
okay, let me check. SIAM portal. I think it has not yet been released.
Okay. No, I have not received any kind of mail or kind of yes.
So you can see here
Exam format
exam
I have.
form.
Yes. Yes. That
Type
I
of
received.
exam you have to be appear. Physical calculators are not allowed. On-screen calculator demo link. Type of exam pen and paper. So you have to
No, it is
see.
not pen.
So computer based, right?
Yes.
I think it has not been yet released.
Okay.
So here it will you will be notified here on.
Okay. Okay.
So last message came related to this on the 31st
Yes.
March,
Yes.
a few days back. Maybe yeah.
So
So it will
it
be
is
released soon.
Yes, it is showing that this the documents that I have submitted, no, it is under verification still.
Okay, 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 okay. So maybe that when that will be done, so they will, I think, uh,
Okay.
provide. Okay, then. So with that, let us end today. Thank you for joining. Hope your doubts have been cleared. And if not, we will meet again on the next day. We'll
Yes.
discuss even a bigger problem like naphthalene. Okay,
Yes. Yes.
and hope that thing will be cleared that time. Okay, with that, let us stop today.
Good night.
We'll meet. Good night. Meet tomorrow. Meet on the next day.
Yes.
Thank you for
Yes.
joining.